Hello, hello. Hope I'm live. Today, my plan is to kind of read all of Circuit Thread. So, with the last few streams, I think two streams, I read the first one, right? We read it, Introduction to Circuits. So, in the stream, I want to, I want to like read each of these papers in depth, right? But my college project kind of wants me to know all of that, and I don't have the time to read everything in a very depth manner. And these are very time consuming papers, but they're long and they're tough to read. So I thought of I want to read everything well, and I will do that. But before doing that, I'll do that later. Before doing that, I'll just speed run through all of these papers, like just get an understanding of what this is about and all. That is the plan for today. Before starting, I kind of want to ensure that I'm live. Yeah, that looks right. So yeah, I don't know what to do now. I think I'll just start. So this is a circuit thread from Distill. We read the first part, right? Uh, this is a summary. So what is it called? Like, what is this thing called? Thread one thing. So I'll just start with thread one. Like, introduces the concept of features circuits and universality in neural networks. That's true. So what did the first paper talk about? The first paper described features. So what is a feature? A feature is what do you call it? It can be described as a direction in a vector space, right? It is like a what do you call it? A couple of neurons which, when combined together, does some very simple tasks such as curve detection or straight line detection, edge detection, things like that. But now when we mix couple of features together, like curve detectors, straight line detectors, another curve detector, then maybe wheel detectors, window detectors, and more, put them together in a peculiar way, they form circuits. And circuits can detect complicated things like, honestly, maybe like wheel detectors are a part of circuits. Huh? They can do complex things like wheel detectors. Yeah, that is not. I don't think there is a like correct what do you call difference between feature and a circuit. Like, it is not explicitly defined, but it's more of a, yeah. This is a circuit. This is a feature, and this one is a circuit. So that is circuits and features. And then the paper, yeah, that's it. Then the paper talk about universality of some features or features and circuits in neural networks. So the paper states that like every uh, let's say image based model will start with edge detection neurons. It is the paper states that it is a universally accepted thing. The paper wants to extend that thing to be like every image model has a curve detector and so on, like in a higher level things. That's what the paper wants. So the paper talks about that. So yeah, I'm kind of struggling to communicate these things. I don't know why. Wait. So what does the paper? What is universality according to the paper, right? The paper is trying to say that some features and circuits are universal across every neural network working on the same domain, or maybe even different domains. Yeah, nailed it. So that's the plan. So that are those things, right? Now, I think we can move on to thread 2. And from these threads, I don't think I will be able to like, read through every line. I'll be skimming through, quickly going through all of these. And hopefully, if I'm able to complete all these, I kind of want to start reading the, what do you call it? Anthropics circuit thread. Yeah. But I think that is a very hopeful statement. Wait, April 2021. Okay. That's all I say, man. Wait. Part of circuit thread, blah, blah, blah. Okay. We read this. Okay, the first few articles of circuit project will be focused on early vision in Inception V1. For a purpose, the 5 convolution layer leading up to the third polling layer. Okay, so the thing is, I don't know what is Inception, right? So let's skim read that paper now. I think I have it downloaded now. Yeah, there you go. Going deeper with convolutions. We propose a deep CNN architecture codenamed Inception, which is responsible for setting a new state-of-the-art classification detection in ImageNet large-scale visual recognition challenge 2014. 2014? Uh, in chronological order, tell me about the common deep learning models for images like AlexNet, ResNet, etc. Length, always CNN, developed by, oh, Jan Lake, okay, him. Okay. Then AlexNet in 2012. ZFNet improved AlexNet by visualizing internal features. Okay. VGGNet 2014. GoogleNet or Inception. Oh, is the paper by Google? It actually is, man. Yeah, I didn't know that Google created Inception. Introduce Inception modules with parallel convolution. Okay. Microsoft residual network solved vanishing gradient problem. Oh, then they introduced Inception V for Inception ResNet. Combine Inception modules with residue. Okay. Then DenseNet, MobileNet, FHANet. Then in 2020 we have Vision Transformers. 2022 modern Zen architecture incorporating transformer inspired design choices while maintaining convolution operation. Okay. So what is this thing saying? Oh, similar. Then AlexNet in 2012. Is that a net? I've never heard of that thing. Oh, there. That's how the ZF comes from. Then we have VGG, Inception, ResNet. So ideally, so Inception probably doesn't have ResNet, right? This paper was published in 2014. Okay. For this thing, so okay, now describe in detail Inception V4 V3. It's like yeah, I think I would do mobile net efficient vision transformer, swing transformer, improved VIT with hierarchy of feature interaction for better efficiency. Con next, which is the best today? Yeah, I mean, obviously. Balance of accuracy and efficiency, efficient. Con next provides stronger performance with inductive, okay, for deployment on edge devices. For transfer learning and general purpose use, ResNet and EfficientNet. EfficientNet is everywhere. Huh? That is probably the best. I don't care about resources. I want the model that gives the highest accuracy. Convolution enhanced vision transformers. Hmm. Yeah, I think it's just vision transformers. Vision transformers. The 3 billion parameters currently hold several benchmark records. Yeah, I can just look at benchmark records, right? Uh, what is it called? Image benchmark results. Yeah, we will continue reading the paper, but give me a sec. Oh, ImageNet benchmarks. Okay. What the hell is this? What? Why is Victor here? Moderator? Hmm. There's a lot of parameters. Coca. What is that? Yes, yeah. Contrasting captioners is an important vision language model by Google in 2022. It combines contrastive learning and captioning objective in a single framework, allowing it to excite both vision language understanding and generation tasks. Dual encoder architecture with vision encoder and a text encoder uses contrastive learning to align visual and textual representation. So, okay, now let's move on to Inception, right? Now, okay, let's start going deeper into Inception v3. 2015. Improved version of Google Earth's Inception architecture designed to enhance accuracy while keeping computational efficiency in mind. Factorize convolution for efficiency. Instead of using convolution filters, I think I should start with Inception v1. Okay. Now describe Inception v1. 2014. This came in 2015. Okay. Then where is Inception v2? Also on GoogleNet. Oh, that's kind of cool, right? GoogleNet. Okay. Was introduced by one image challenge with the top 5% error rate of 6.67, significantly better than LexNet and VGGNet. Okay. 6.67 top 5 error rate. Okay. Inception module. Okay, they use multiple scales. One by one convolution reduces dimensionality and adds non-linearity. 3 by 3 convolution, medium scale features, large scale features, max pooling, spatial information extraction. Output from all these branches are concatenated, helping the network learn diverse features efficiently. Okay, that's kind of cool. Okay, one by one convolution. How does one by one convolution reduce the dimension? Dimension reduction. One by one convolution applies filter that have been okay, but can vary in number. Each filter combines information across channels in a single spatial location. It creates a weighted sum of the input channels, suppressing that information into fewer output channels. Uh, like, how is that possible, right? Is there stride? No, there's no stride involved in what? I was expecting stride to be existent. Each filter produces a single channel in the output. Why using filter? The input channels, you can reduce dimensionality. I think I'll Google it. Okay, convolution step at 3D input with filter 3 by 3 by 3 will have a filter striding. In other words, one by one convolution was used to reduce the number of channels while introducing non-linearity. One by the channel means the filter size of L, that means a single number as opposite matrix. Okay, this one by one filter will convolve around the entire input pixel by pixel. Change the example, each one which would be this. The output will have the same height and width, but only one channel. Oh, it will reduce the channels, I. Okay. It doesn't reduce dimension, it reduces channels, which essentially reduces dimension. I mean, which is the dimension, right? Okay. Hmm. Makes sense. Cool. I'm fine with that. Auxiliary classifier, small networks attached to intermediate layers. Uh, Inception V1 architecture image. Hmm. Hmm. Caption module, auxiliary classifier, global average pooling. Yep. Auxiliary polling is attached to intermediate layer. Mm-hmm. There will be gradient propagation and act as regularizer to prevent orbiting. These classifiers are discarded during inference. Auxiliary classifier improve gradient flat regularization. Two auxiliary classifiers attached to intermediate layer they help with gradient propagation and cast regularizer to prevent overfitting. They help with gradient propagation and act as regularizer to prevent overfitting. These classifiers are discarded during inference. Hmm. Okay. There are these things. They help with gradient propagation, act as regularizer, and discarded during inference. Okay, I'm fine with it. Sure, some kind of regularizer. Okay, cool. Global average polling instead of fully connected layers. Instead of 10 fully connected layers, global average polling is applied. This reduces parameters significantly, making the network more efficient. Okay, so if we just versus fully connected network compare average all values in the page to a single value per channel. Parameter 0. Okay. No learner parameter. Okay, for the connection layer, I know that. Parameter efficiency, regularization effect, network interpretability. Okay. Structure constraint, adaptability. Okay. Modern CNN often use gap followed by a single fully connected layer. Okay. All CNNs. Network with gap generally generalize variety. Then why don't we use gap with the transformers? Vision animals are used gap for several reasons. Token based representation. Transformers work with sequence rather than feature maps. Oh, one message remaining. Come on, man. You want to tell me earlier, and I wouldn't have used you. The CNS token or classification token in the IT already serves a similar purpose. Hmm. CNS token transformers already provides a more powerful aggregation methods and gap. And as it learns to weigh the importance of different parts of the input through the admission mechanism, rather than giving equal weight to spatial position. I don't get it. I think I have to use something. Give me a sec. Gemini. Yeah, put you here. Uh, 2 point of flash. Yeah, that would do. Why don't we use gap with transformers? Okay, what did you say? Uh, okay, you said something stupid. Okay. General adversarial pixel. I don't think that's what it means. Global average pooling. I'll start. New, new, new. Okay. Why global average? Okay. Traditional CNNs. Why? What is that thing? Again, traditional just use. Oh, I can do that. Oh, okay, that's cool. A gap is a technique used to replace fully connected layers at the end of the network. It calculates average activation. Okay, sure. Why? Okay. Transformer process happens differently. CNN produce images by convolving filters, inherently capturing spatial hierarchies. Transformers break image into batches, tokens, and process them with self-attention mechanism. They don't rely on the same hierarchical spatial relationship as CNNs. Okay. Loss of personal information. While gap pools spatial information, CNNs retain some personal information through convolution loss. Transformers on that. Okay, you just can't use it. Okay, cool. I'm fine with that. So V1's architecture, initial convolution layers, then multiple inception modules, then auxiliary classifiers. What is auxiliary classifier? Oh, this thing. Okay, actually, irregularizer. And global average polling and softmax. That's cool. One image at 2014, 12x few parameters and VGG. Ooh, that's neat. 5 million? That's low, man. Exception. Manually design inception module, no automated architecture search. High memory consumption due to multiple path convolution. 5x5 convolution is expensive. Late optimizing Inception V3. Would you like a PyTorch or TensorFlow implementation? Maybe not now, but probably I will want to. Okay, Inception V3 is an improved version of that thing. Okay. Key features. Factorized convolution for efficiency. Instead of using large convolutions, V3 factors them into smaller, more efficient convolution. 5x5 is replaced with two consecutive 3x3, reducing computational cost while maintaining similar expressiveness. Okay. Asymmetric convolution. A 3x3 convolution can be split into separate convolution, 1x3 convolution, 3x1 convolution. This reduces number of parameters and speeds up training. Okay. Auxiliary classifier reduces auxiliary ELME includes. Okay. Sure. Label smoothing, efficient grid size reduction, batch normalization. Architectural breakdown. We get it. Okay, so now that we have an okay understanding of what inception is, just ensuring this thing is okay. That looks okay. Now that we have all that, um, I want to go here. Okay. First two articles of Circle Pi will focus on early vision on Inception V1 for a purpose of five convolutional layers leading up to the third polling layer. For purpose, the five convolutional layers leading up. Yeah, that's cool. Oh, okay. Other cause of the layers will see networks go from raw pixel to sophisticated boundary detection. Okay. Talk, uses Inception V1 as the foundational model to perform interpretability research. Sure. And the way intermediate features like complex carbon detectors, black versus white color detectors, small circle formation from cars. Studying automation has two major advantages at starting. Okay, it's particularly easy to study. It's close to the input, and the circuits are only a few layer deep. But isn't that many neurons? What do you mean? Common for vision models to have been the order of 64 channels in the initial convolution layer, which are applied at many spatial positions. So there are many neurons. The number of unique neurons to be smaller. Okay. You're saying that they will be kind of similar. Early vision models seems most likely to be universal. They have the same features and circuit from across different architectures and tasks. Broad overview. Okay. By limiting ourselves to early vision, this article only considers the first 1,000 neurons of inception V1. But our experience is that 1,000 neurons is more than enough to be disorienting when one begins studying a model. Our hope is this article will help reader avoid this disorientation by providing some structure and handholds for thinking about them. Oh, mentally, okay. Sure, uh-huh. Hmm. Many neurons in vision models seem to fall into the families of similar features. Hmm. Okay. Sure, we're categorizing of units in the first five layers of inception V1. This article shares the working categorization of units of the first five layer. Okay, sure. Caveats. Okay. Our view, we are also understanding how the computer model features protein circuits consider a neuron, the unit and strongest. Hmm. The first convolution layer of every model we have looked at is mostly composed of two kinds of features: color control detectors and Gerard filters. I'll just put you there. Hmm. They're messy. It seems like it's this is a result of the gradient not reaching the RLS very well during training. And the inception viewpoint products the adoption of modern techniques like mass normalization and ADAM. Okay, no ADAM, huh? Which makes it much more easier to training deep models. Okay. One subtlety that's worth noting here is the Gabor filters almost always comes in pairs of weights, which are negative versions of each other. What inception viewpoint? Okay. Fills in holes allowing for the information. Hmm. And I'll come back in a second. Right? Give me a sec. Hey, so that went a bit longer than I anticipated it to be. Give me a sec. Where was I? Hope my audio is well. So yeah, we learned Inception, and this is a second lab. Uh-huh. In convolutional 2D1, we begin to see some of the classic complex features of visual neurons. Hmm. Complex Gab. What are garbars? Garbars. Filter, yes. Analyze the frequency and orientation of image. Linear filter. Using edge detection. Cool. Low frequency. These ones seem to respond to lower frequency edge pattern. In addition to complex audio, set a variety of features including more invariant color contrast detectors, Gabber-like features, and all. Okay. Counter 2D, we see emergence of very simple shape predecessors. This version is the first unit that might be described as line detectors, preferring a single long line to Gerber patterns and accounting for about 25% of the units. We also see tiny curve detectors. One fun aspect of these features is that you can see that they are assembled from Gerber detectors in the feature visualization, with curves being built from a small piecewise segment. Okay. Infinity 3 had significant increase in diversity of features that we observe. Some of them, hmm, this paper talks about what are the features that they observed in the first five layers of inception. Black and white detectors, small circle detectors, triangle detectors. Triangle detection often said to be just a multi-edge detectors downstream or in conjunction with the hmm. Mixed 3B shaded two layers of abstraction. On one hand, it's on some quite sophisticated vision. Boundary detectors. One of the most striking transition is the formation of boundary detectors. When you look at the feature visualization dataset example, you may think as another iteration, but they are in fact combining a variety of cues to detect boundaries and transition. Okay. For detectors, prototype header, the goal of the was to give a high level overview of our present understanding of audio vision inception we want. every single feature discussed in the article is a potential topic of deep investigation. For example, are the curve detectors, what types of feature they fire for, how do they behave on various edge cases, are they built? Our the coming articles will go deep. We will do deep dives, rigorously investigating these questions for a few features, starting with curves. Our investigation into early vision has also left us with many broader open questions. I mean, to what extent do these feature family reflect fundamental questions and features versus a taxonomy that might be helpful for humans? Hmm. Why do features often seem to form in families? Features often seem to form in families. Sorry, that's the first one. Or it looks okay. Yes, curve detectors. Um, Every vision model we have explored in detail contains neuron which detect curves. Window two. Curve detectors. Every vision model we explored in detail contains neurons which detect curves. Hmm. Curve detector and vision model have been hinted in the literature as far as 2013, and several neurons have been studied carefully in neuroscience. We briefly discussed curve in our first earlier area for early vision, but okay. So we are going moving deeper into curve detectors. I mean, I don't know how much I want to. Hmm. Interpretive community disagrees on several critical questions. In particular, are neural network representation composed of meaningful features? These features ranking articulable properties of image. Or the on the one hand, there are a number of papers reporting similarly meaningful features. At the same time, the significant amount of skepticism only partially reflected on the literature. One concern is that the feature which seems superficially to be meaningful may in fact not be what they appear. Several paper has also the neural network primarily detect textures or imperceptible patterns rather than the kind of meaningful features described earlier. Finally, even if some meaningful features exist, it's possible that they don't play exceptional role in network. Okay, simplified stories of curve neurons. Before running detailed experiments, I'll look at the high level and slightly simplified story of how the curve 10 neurons in 3B work. Each curve detector implements a variant of the same algorithm. It responds to a wide variety of curves, preferring curves of a particular orientation, gradually firing less as the orientation changes. Curve neurons are invariant to cosmetic properties such as brightness, texture, and color. Hmm. Curve detectors sparse activation firing in response to only 10% of spatial position. those ImageNet and usually activating weakly when they do fire. When they activate strongly, this in response occurs with similar orientation and curvature. Okay. There's no explicit incentive for the network to form meaningful neurons. True. Inception Vision is trying to classify images into categories, many levels of abstraction removed from curves, and somehow curve detectors fell out of the gradient descent. Yeah. While detecting curves across wide variety of natural images is difficult and arguably unsolved problem in classical computer vision. Everyone seems to learn a flexible and general solution to this problem, implemented using 5 convolution layers. We'll see in the next article that the algorithm uses straightforward and understandable, and since we have re-implemented it by hand. Wow. What exactly are we claiming? So these neurons detect cause. We think the part of the distance that is sometimes disagreement about whether neuron detects particular stimulus is that there's a variety of claims one may be making. It is easy. It's pretty easy to show that empirically, when a neuron detector fires strongly, the stimulus is a reliable curve. It's pretty easy to show that empirically, when a curve detector fires strongly. Okay, but then there are several other claims that might be more contentious. Contentious? What does that mean? Likely to cause arguments. Causality. Curve detectors genuinely detect a curve feature rather than other stimulus. We believe our feature visualization and visualizing attribution experiment establish a causal link. What? Curve detectors genuinely detect a curve feature rather than another stimulus correlated with curves. Hmm. We believe our feature visualization and visualizing attribution experiment establish a causal link since running in reverse produces a curve. I don't get it, but this is not the stream to go behind that. So detection responds to a wide variety of curve stimuli, generality, purity. Okay. Hmm. Feature visualization uses optimization to find input to a neural network that maximizes given objective. But we'll use the objective throughout the article. One reason feature visualization is powerful is it tells about causality. Since the input starts with random noise and optimizes pixel rather than a generative prior, we can be confident that any property in the resulting image contributes to the objective. Ready feature visualization is a better skill, and the image might feel disorienting if you haven't spent much time with them before. The most important thing to take away is the caution. You may also notice that there are bright opposite hue colors on each side of the curve. This reflects a preference to see a change in color at the boundary of the curve. Finally, if you look carefully, you'll notice small lines perpendicular to the boundary of the curve. You can call this weak preference for small perpendicular lines combining, and we'll discuss it later. Hmm. Okay. Every time we use feature visualization to make a curve neuron far as strong as possible, we get images of curves. Even, even when we explicitly incentivize the creation of different kinds of images using diversity team. This strongly this is a strongly evidence that curve detectors are polysemitic since we usually use it. Roughly equally perforing different kinds of similar. So that I'm at neurons, huh? Not like features. Features are neurons. Curve detectors. What does curve detector mean here? Features or neurons? Probably neurons, not features. Features are not polysemitic, right? Like features are things that do one thing. As they might also be polysemitic, huh? One feature detects wheels and cows. That can happen. But if that is the case, maybe we are taking the feature wrong. Like that might not be the correct feature. Anyways, as we study the data set, we will focus because also tools we use for studying neuron families, including feature visualization, can be used in context of particular image using attribution. There's a significant amount of work on how to do an attribution in neural networks. These methods attempt to describe each pixel or earlier neurons. Attempt to describe which pixel or earlier neurons are responsible causing neurons to fire. Nick, okay, the author of this paper manually labeled our 800 images to four groups: curve, imperfect curve, unrelated image, or opposing curve. We randomly sample a fixed number of images from the bin, while labeling Nick could only see the images pixels, not additional information such as the neurons activate. Okay, here's the following rubric for labeling. Cause, okay, sure. We compare our label activation across the same images. Using a stack plot, we see the different labels separate cleanly into different activations. Hmm. So there are many images that cause neurons active but aren't classified as cause and perfect cause. When we visualize, we see that the image contains several curves. Mm. When we visualize attribution, we see that many of them will contain curves. Hmm. He found it hard to detect sample curves across hundreds of curve images because he started to experience the after image effect that occurred when looking at kind of similar for long. As a result, he found it hard to tell whether subtle curves were simply percep- perpec- perceptual illusions. I'm on a different point on the activation spectrum. These charts will help. These charts are helpful for comparing or unlabeled labels, but they give an incomplete picture. From this perspective, we can see the case where our neural fires strongly. I think what if And if a neuron frequently barely fires, how important is that for understanding the role of a neuron in the network? Hmm. The first experiment suggests that the call detection responds to cause a different orientation. While the dataset gives almost every image of curve, they don't come labeled with data such as orientation or radius, making it hard to answer the question that requires systematically measuring responses to visual properties. How sensitive are curve detectors to curvature? Blah 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 blah. Okay. Since dataset example contain curve detectors, since dataset examples suggest curve detectors are most sensitive to orientation and curvature, we will use them as a parameter in our curve renderer. Hmm. We find that simple drawing can be extraordinarily exciting. The curve image that causes the strongest excitation up to 25 standard deviation above the our dataset activation of similar orientation curvature to neurons feature ratio. Sharp. Why do we see discrete triangles? Well, these are just okay. Extreme curve neurons partially respond to edges. Okay, same thing with edges. Hmm. Radial tuning curve. Given a positive activation to synthetic stimuli, we can render multiple neurons on the same circle. Hmm. Okay. Man, I don't think I want to read more. Whoa. Yeah, by example, we manipulated butterflies and cars without having to worry about the details of ether. We delegated the intricacies of recognizing butterfly of many species and orientation to the neuron, letting us work with the abstract concept of butterflies. Okay, I think they made a neural network that classified butterflies, and some neurons learned this, like the shape of butterflies. We think this is one exciting way to fuse classical computer vision with deep learning. There's a plenty of low-hanging fruit in extending the techniques shown above, as our spline parameterization is just an early prototype and optimization are using a neural network that's just half a decade old. However, we are more excited by investigating of how user can explore the space between tasks than improvements in particular tasks. Investigate how users can explore the space between tasks. Hmm. Once a task is set in stone, training your network for the exactly that job will give the best results. In real world, tasks are rarely specified with precision. The harder challenge and the harder challenge is to explore the space of task from okay. Monkey weaver. Computer field like neuroscience and artificial neural networks make careful investigation easy. That is true. We can read and write every weight of the neural network, use gradients to optimize stimuli, and analyze billions of realistic activation across datasets. Compassing these tools let us run a wide range of experiments that shows us different perspective on a neuron. If every perspective shows us the same story, it is unlikely we are missing something big. Compared to if you want to invest, it may seem odd to invest it. Composing these tools let us run a wide range of experiments that shows us different perspectives of a neuron. If every perspective shows us the same story, it's unlikely we are missing something big. Hmm. Given this, it may be odd to invest so much energy into doing a handful of neurons. We agree. We first estimated it would take us a week to understand the curve family. Instead, we spent months exploring the fractal of beauty and structure we found. Hmm. Many paths led us to techniques for studying neurons in general, like synthetic stimuli or using circuit editing to ablate neuron behavior. Others are only relevant for some families, such as equating. A couple were curve specific. Okay. A broader goal is to fully reverse engineer neural network. It may seem concerning that studying just one family took so much effort. However, from the experience of studying neuron families at variety of depth, we found that it's easy to understand the basics of a neuron family. Apply a microscope shows you feature visualization, dataset sample, and soon waits in a few seconds. Since feature visualization shows strong evidence of causal behavior and dataset examples, this is actually strong evidence of what. While it is usually possible to understand the main function of a neuron family at a glance, researchers engage in closer inquiry of neuron family will be rewarded with deeper beauty. While it's usually possible to understand the main function of a neuron family at a glance, researchers engaging in closer inquiry of neuron family will okay. When we started, we were nervous that 10 neurons was too narrow of a topic for a paper. You know, I realized, but now we realize a complete investigator would take a book. Hmm. Okay, curve detectors. Building blocks of interpretability. Interpretability techniques are normally studied in isolation. We explore the powerful interfaces that arise when you combine them, the rich structure of combinatorial spaces. By combining feature visualization, what a neuron is looking for, with attribution, how does it affect the output? We can explore how the network decides between levels like dogs and cats. Hmm. Hmm. The growing success of neural networks are corresponding need to be able to explain the decisions, including building confidence about how they will behave in the real world, detecting moral bias, and for scientific curiosity. In order to do so, we need to both construct abstraction and reify or reinstate the literature interfaces. With a few exceptions, existing work interpretability fail in these concepts. Machine learning computers primarily focus on developing powerful methods such as feature visualization, attribution, and dimensionality reduction for reasons about human networks. However, these techniques have been studied in isolated threads of research, and the corresponding work of reifying them have been neglected. Human computer interaction communities has begun to explore its user interface for neural networks. We have been left at in this article, we treat existing interpretability method as a fundamental and composable building blocks for rich user interfaces. We find that these disparate techniques now come together in a unified grammar, fulfilling complementary roles in the resulting interfaces. Moreover, this grammar allows us to systematically explore the space of interpretability interface, enabling us to evaluate whether they meet particular goals. We present interfaces that show what the network detects and explain how it develops its understanding while keeping the amount of information humans get. In this article, we use GoogleNet, an image classification model, to demonstrate our interface idea because neuron seems unusually semantically meaningful. Although we have made a specific choice of task and network, the basic abstraction and pattern for combining them that we present can be applied to neural networks in other domains. Although here we have made a specific choice of task and network, basic abstraction and pattern of combining them that we present can be applied to neural networks in the domains. Hmm. Any kinds of illness. Hmm. Skim through. What does the network see? A tiger cat feature is like nowhere to be found, right? Yeah. Hmm. Okay. I'll be back in a second. Give me a break. I'll be back. 10 minutes. Hello, hello. All right. So, um, I've noticed something. So, this one, which I was trying to read, is this is not actually a part of the circuits thread, but the building. Yeah. If I type another name, weight, banding. Yeah, I get it. Yeah, this is not actually a part of the circuits thread. This is kind of a what tool which can be used to be good. Very good. Tool which can be used to visualize double things. So I don't think it makes sense reading this. We saw that, right? Like these parts. Yeah, I think I'm going to skip this one. Right. Naturally occurring equivariance in neural networks. So this is the one. I think I have to rename this. My already signed, right? Yes, sir. So naturally occurring equivariance in neural networks. Convolution neural network contains a hidden world of symmetrics within themselves. The symmetry is a powerful tool in understanding the features and circuits inside neural networks. Symmetry. Hmm. I think I'll put that the incidence features often occur in symmetric manner. Uh, to see these symmetries, we need to look at the individual neurons inside the convolutional neural network and the circuits that connect them. It turns out that many neurons are slightly transformed versions of the same basic feature. This includes wait, are features neuron like, differentiate what do you call features and hmm, features and circuits? Absolutely, okay. Specific values are properties that a neural network learn to recognize and process. Think of them as building blocks. Lower level edges. Group of neurons. Wait. So does each neuron represent a single feature? Well, as a simplification, it's not actually entirely accurate. Okay. There are cases. In summary, when then what's the difference, man? How am I simplified? Okay. Feature circuits. What information is being presented and processed? How the information, bro, that's just wrong, right? Higher level, more abstract concept pattern. Okay, this is just wrong, right? Okay, bro. Gemini sucks. And turns out that many neurons are slightly transformed versions of the basic features. Rotated copies of some same feature. Okay. Copies, features, detecting different colors, much more. I think I'll just put you somewhere here. Equivariant features. Rotational equivalence. One types of equivalence is rotated version of the feature. Okay, so equivariant feature. There is rotational equivariance. Scale equivariance. Hue equivariance. Okay. For color detection feature, you often see variants using the same thing in different hues. What is the hue? It's like the wavelength of the color. Just think of it as a color. Hue rotation equivariance. In early vision models, we often see color contrast units. Okay, color contrast. Sure, reflection equivariance. As we see more mid layers, rotated variants become less prominent, but horizontally flipped pairs become quite relevant. Hmm. I want this thing here too. Miscellaneous. Finally, we see variation of features transformed in miscellaneous ways. Equivariant circuits. The equivariant behavior we observe in neurons is really a reflection of the deeper symmetry that exists in the weights of the neural networks and the circuits they form. These are by focusing on rotationally equivalent features that are formed from rotationally invariant features. This invariant equivariant case is probably the simplest form of equivalent circuits. Hmm. The equivalent behavior you observe in neurons is really a reflection of deeper symmetry. Okay, we'll start. We'll start by focusing on rotationally equivalent features that are formed from rotationally invariant features. High-low circuits. In the following examples, we will see high-low frequency detectors get built from a high frequency factor. Low frequency factor, both factors correspond to a combination of neurons and previous. Hmm. Okay, now we're talking about circuits. Okay, like features, there are circuits. High-low circuit. I will see high-low frequency detectors. Hmm. Contrast center circuit. Same pattern can be used in reverse to turn rotational equivalent feature back to rotational invariant feature. I don't know exactly understand. Black white color feature. I mean, not feature circuit. Line or circle divergent circuits. It invariant feature is very early line, like complex being combined to create a small circle unit. Hmm. Human animal circuit. Hmm. The hell? Okay, bro. Equivariant to equivariant. Equivariant to equivalent circuit. The circuit we are looked so far as invariant to equivalent, or either they had invariant input units or invariant output units. You here circuit. Uh, Circuit connecting two set of few equivalent centers. Okay. I mean, sure, I get it. Equivalent architectures. Focus is normally on designing equivalent architectures rather than natural equivalents. Historically, there has been some interesting back and forth between two. Researchers have often observed that many features in the first layer of a neural network are transformed versions of basic templates. Hmm. Conclusion. Equivalence has a remarkable ability to simplify understanding. Hmm. When we see neural network as a family of features interacting structured by understanding small templates, I can actually turn equivalence is a big help whenever we discover it. Okay. I get why equivariance is so much, why a single chapter is given to the story. Think of understanding neural networks as reverse engineering a regular computer programming. Okay. But natural equivariance does have some limitations such as when equivalent families, like blah blah blah. Perhaps in the future, okay, sure. Blah blah blah. Okay. How you okay? This is probably about how high low frequency detectors, right? Come on, man. I don't want like hmm, bro. Some of the neurons in vision models are features that we aren't particularly surprised to find. Core detectors. Hmm. Fact, you have been discovered animal visual cortex. It's easy to remember. Okay. Higher frequency spin not surprising. There are not a feature that we would have expected a priori to find. Yet, when we systematically categorized the early layer, we found full 50 neurons of mixed 3A that appear to detect high low frequency pattern. One worry we might have about the circuit approach to studying neural network is that we might only be able to understand a limited set of highly intuitive features. So it's possible to understand at least somewhat unintuitive. It's possible to understand at least somewhat unintuitive features. Sure. Function. How can we be sure that high low frequency detectors are actually detecting directional transition from low to high spatial frequency? I mean, visualizing these gets activated. Okay, there might be rotational equivalence in some, might not be in others. Data set wise examples. Hmm. Okay. Synthetic tuning curves. Tuning curves allows us to shows us how a neuron response changes with respect to a parameter. There is standard method in neuroscience. How a high low frequency detectors built from low neurons. EQ, okay. high low frequency factors. Construction of high low frequency. Okay. Usage. High low frequency detectors contribute to a variety of features. Their most important role seems to be in supporting boundary detectors, but they also contribute to bumps and pivot textures. Okay. I want this thing. Johnson feature appear to ignore polarity of a low frequency detector responding. Role in object boundary detection. Universality. High low. Okay. It's always good to ask if we see what we see is a rule or an interesting exception. Higher frequency seems to be the rule. Higher frequency detector seems to be the one. So high low frequency detector similar to the ones in inception even can be found in a variety of architectures. Can again perform NMF on the weight of the higher low frequency detector. Although high low frequency detectors was represent a feature we didn't necessarily expect to find in neural networks, we find that we can still explore and understand them using interpretability tools. We also learned that high low frequency detectors are built up from comprehensible lower level paths, and we have shown how they contribute to later higher level features. Finally, we've seen that high low frequency detectors are common among multiple network architectures. They are highly universal, present in almost all models. And yeah, sure. We might wonder whether the existence of high low frequency detectors isn't so unnatural after all. We have we even find approximate high low frequency detectors in unexpected places with its substantially different training data. Before neural networks, the aesthetic quality imparted by the blurriness of out of focal region of an image is already known as photograph as uh-huh. Okay. In VR, the visual blur can either provide effective depth like a sure, or a frequency detector might well be commonplace in both natural and artificial vision systems as yet another type of information queue. Nevertheless, whether the exchange is natural or not, we find that higher frequency detectors are possible to characterize and understand. Sure. Curve detectors. Wait, what is this? What is this, man? Why is Dark Reader slowing down Firefox? Sure. Please close your eyes. Is there any frame drops or anything? No. Now if I turn this man on. Oh, okay, bro. Neural circuits. We reverse engineer a non-trivial learned algorithm from the weights of a neural network and use it to use its core ideas to craft artificial neural network from scratch and re-implements it. Okay. Many approaches to interpretability gives high-level exceptions, explanations, but hard to know if they're true. Circuits are the opposite approach, building up individual neurons and individual weights to easily verifiable explanations of tiny sizes of neural networks. But it faces a different question. Can we ever hope to understand a full neural network in this way? This paper uses a circuit approach to reverse engineer code detector, a neural family we studied in the previous article. We find that although code detection was more than 50,000 parameters, those parameters actually implement a simple algorithm that can be read off the weights and described in a few English sentences. The reason the curve circuit is relatively simple is because equivalence matter. What was that? Oh, okay, I get it. Equivalence. Rotation equivalence studies. Okay, okay, blah 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 blah. Okay, okay, I get it. While the curve circuit in instruction V1 is quaint next to the 175 billion weights in GPT-3. Oh, GPT-3 is released, huh? It's big step from the tiny circuit in zoom in. Curve detection algorithm. Well, the curve circuit in instruction V1 is quaint next to the sure. Curve detection algorithm. In this article, we are reverse engineering the 10 curve neurons we studied in other, which resides in fifth convolutional layer of inception neuron. Okay. Hmm. Man, I'll take a break again. I'll come at 6. Yeah, my brain cells are degrading. Quick. Alright. See ya.